So in last lecture we have seen the graphical representation of the S.H.M, which has started from the mean position, and in this lecture we are going to see the S.H.M which is starting from the extreme position. This is the representation of the S.H.M which is starting from the extreme position. So for this, if this is a we have taken this as a 0, then let us take this as a. So x is equal to a at a time t is equal to 0. So previously x was 0 at a time is equal to 0 when the particle was starting its journey from here, but now the particle is starting its journey from the extreme position. Therefore we have taken x is equal to a at time t is equal to 0, where a is the amplitude. So amplitude is nothing but the maximum displacement from its mean position, and which we have taken as a. Now we know that the general equation for the displacement is a sine omega t plus alpha. Now if we are putting the value of this t is equal to 0 and x is equal to a, we are going to get the equation for the displacement starting from the extreme position. So let us put these values. X is equal to a into a sine of this omega t, this will become 0, so alpha. So we can say that this sine alpha is equal to 1. When this sine alpha is equal to 1, alpha can take the values of pi by 2 or 3 pi by 2 and so on. Okay, so if I put the value of this alpha as pi by 2 in this equation, so I can write it here as x is equal to a sine omega t plus pi by 2, which is nothing but the a cos of omega t. Now this is the expression for the displacement of a S.H.M which is starting from the extreme position. Now let me write this equation over here. So we have got x is equal to a cos of omega t. So this is the expression for the displacement. I can write velocity from this. So rate of change of displacement with respect to time is nothing but the velocity. If I take differentiation of this, so minus a omega sine omega t, this is nothing but the velocity, and acceleration will be minus a omega square cos of omega t. So this will be the acceleration, and we can have the graphical representation similar to the what we have seen previously. So time period t is the time required for a complete one oscillation, and during this time period t there is a phase change for the 4 times. And now we are taking those main 4 points. Now let us draw the displacement vector. We know that displacement vector is changing from a to minus a. As this is a cos wave, it is not starting from the 0. Suppose this is a t. Now this will be t by 2. This will be t by 4. And here it will be 3t by 4. So this t represents the phase of 2 pi. This will represent the phase pi, pi by 2 and 3 pi by 2. So these are the different phases at a different time intervals. So at a time t is equal to 0, as this is a cos wave, it will not start from here. So we know that this cos 0 is equal to 1, therefore x is equal to a, so its journey will start from here. Then cos of 90 is equal to 0, so it will become 0. Cos of pi is equal to minus 1, so it will become minus 1. And cos of 3 pi by 2 is 0 again, so it will be 0. And for 2 pi it will become again a. So this will be the graphical representation of the displacement vector, and it will repeat once again as it is. Okay, so this is the displacement vector for the S.H.M starting from the extreme position. We can also draw the velocity vector. So the velocity vector is changing from a omega to minus a omega. So this will be t by 2, t by 4, 3t by 4. Once you know the relation between the time period and phase change, and if you know the table of the sine and cos at the degrees from 0 to 360 degrees, you can draw these graphs very easily. Okay, so this is related to pi, this is related to 3 pi by 2, and this is related to the 2 pi. Okay, now as this is a sine wave velocity, so this is a velocity. So the velocity vector is a sine wave and it is starting from 0. So at a sine pi by 2, we know that sine 90 is equal to 1. Therefore it will be minus a omega. So minus a omega, I will take a little bit downwards. So this will be the point. So this will be minus a omega. Sine of 180 is equal to 0, and sine of 3 pi by 2, it will be minus 1. So this minus and minus will become plus, and this will be the point. And the sine of 2 pi, so that will be 0. So the point will again come over 0. So this is how it is going to be, and the same will repeat afterwards. Okay, so this is a sine wave representing the velocity vector for the S.H.M starting from the extreme position. Similarly, we can also draw. Now I think you have understood the concept of, or how we can draw this graphical representation of this displacement, velocity and acceleration. Now this is the acceleration. We know that these values will range from a omega square to minus a omega square, and but obvious this is a t, this is t by 2, t by 4, 3t by 4, and the value, these are the related to the phases. So this is related to pi by 2, this is related to pi, 3 pi by 2 and 2 pi. Now we know that this is a cos wave. It will not start from 0, because the cos 0 is equal to 1. At a 0, at 0 cos omega t, so it will be minus, here it will be, okay. Then at pi by 2, so it will be 0. Pi, it will be plus 1. Okay, 3 pi by 2, it will be 0 again, and at 2 pi it will become 1, so it will be minus 1 over here. So the graphical representation will be like this. Okay, so this is how we can represent the displacement, velocity and acceleration of the S.H.M starting from the extreme position. Once you know the these three equations, okay, or even if you know this x is equal to a into sine of omega t plus alpha, and if you know what are the condition for the particle starting from the mean position and the extreme position, we know that for the particle starting from the mean position, you just take x is equal to 0 for t is equal to 0, and if you put these two values into this equation, you are going to get x is equal to a sine omega t. And for the particle starting from the extreme position, just put the condition x is equal to a at time t is equal to 0, and if you put these two values in the same equation, we are going to get x is equal to a cos omega t. And once you know the displacement, so this is for the mean position and this is for the particle starting from the extreme position. Now once you know this displacement vectors, you can calculate the velocity and the accelerations. And if you know the relation between what is the time and the phase at that particular time, so when you can say that when this time is equal to t by 2, that t by 2 is related to the phase of pi. Okay, when this time is completely t, that is related to the 2 pi. Once you know the relation between this time and phase, and if you know the relation of the displacement vector, you can draw this all 6 diagrams, the 3 which we have seen in the previous lecture for the mean position and these 3 for the extreme position.